Hi everyone, welcome to week 11. We are going to be studying something called vectors, and in doing so, we're going to use some of the tools that we have been learning this semester, including Pythagoras theorem, trigonometric ratios, introduction, scalars versus vectors. Now, there are some phrases that are complete in itself, like if I say 10 oranges, then you know what I'm talking about. But some that are not complete in themselves. For example, if I say wind speed of 12 miles per hour, you can still ask in what direction, meaning that the information of how fast the wind is going is not enough because you also want to know what direction it is going in. This means we can classify quantities into two groups: a scalar, which is concerned only with how much or how many, and a vector, which is concerned with how much, how many, as well as in what direction. Example: weight, temperature, humidity. These would be scalars. Speed, acceleration, force would be vectors. Notation and representation. A vector A would be denoted by A with an arrow on the top, and then we draw vectors using arrows. This part is called the tail of the vector, and this part is called the head of the vector. The first thing we're going to learn is how to add these vectors graphically. There are two methods. The first is called tail to head method. Suppose A to B are two vectors and you want to find what A plus B looks like. We align A, B such that the tail of B coincides with the head of A. And when you do that, if you connect the initial point to the final point with an arrow, that vector is going to be A plus B. It's kind of like saying if I went from initial point, if I walked along A and I walked along B, it's the same as if I walked from starting to the final point. The second one is called tail to tail or parallelogram method. In this case, you align the vectors A and B so that their tails touch each other. And then you construct a parallelogram. Remember, a parallelogram is a figure in which the opposite sides are parallel to each other. Once you have the parallelogram, A plus B will be the diagonal. Again, recall the diagonal of a parallelogram is a point connecting the opposite ends of the parallelogram. Okay, components of a vector. Now we can apply the addition law in reverse as follows. Let's say I'm given a vector A. The question is, can I find two vectors, one on x-axis and the other on y-axis, so that their sum equals A? Yes. How? Is we take the vector A, I drop 90 degrees on the x-axis, and I call this vector AX. And I drop a 90 degree on the y-axis, and I call this vector AY. Now because this is a square, which is also a parallelogram, by the parallelogram law, AX plus AY is going to equal A. The AX vector, here the x indicates that it lies on the x-axis, and it has a special name which is called the x component of vector A. AY indicates it lies on the y-axis and it's called the y component of the vector A. Now some more notation. For a given vector, we know how to write the vector A with an arrow on top. If you put two vertical lines around it, that is called the magnitude or the value. And theta, subscript A, is called its direction. So on the diagram, if you have an arrow and that vector is A, the length of the arrow, which is written as absolute value or vertical lines A, is called the magnitude. And the angle it makes with the positive x-axis, theta sub A, is called its direction. Now that we have lengths and angles, we can define a way to find AX and AY. Now if you look at here, this is a right triangle. What is sine of theta sub A? Remember SOHCAHTOA? Scratch that. Let's go with cosine. It's going to be adjacent over hypotenuse. What is adjacent? Adjacent here is exactly the length of the x component, and the hypotenuse is the length of the vector. This means that the x component can be found out by taking the magnitude of the vector and multiplying it by cosine of theta a. Now, if this is theta a, um, this angle is also going to be theta a because these are parallel and this is a transversal. Again, recall from earlier weeks, we know that alternate angles are equal, which means that in the other triangle, sine theta a is going to be the y component over magnitude of a, or we get that the y component is a times sine of theta a. In conclusion, what we have is that given a vector a, namely its magnitude and its direction, we can find the x component, which is called ax, so that the magnitude is the magnitude of a times cosine theta a, and the y component, which is ay, as the magnitude of a times sine theta a. In relation to previous topic on trigonometric angles, remember how we had a all positive in the first quadrant, sine positive, tangent positive, cosine positive. If I take a vector here, the x component is positive and the y component is positive on the first quadrant. If I take a vector in the second quadrant, my x component is negative, my y component is still positive. And this makes sense because cosine is negative in the second quadrant. In the third quadrant, my x component is negative and my y component is negative, which again makes sense because both sine and cosine are negative in the third quadrant. And in the last quadrant, my x component is positive and the y is negative, which makes sense because sine is negative. Next week, we're going to learn how to numerically add two vectors, not just graphically, and we will be using the components of the vector to do that.